Okay, so now let's talk about isomerism. Okay, so isomerism is the property wherein iso is same, mer is unit. Okay, so it basically means same molecular formula. Okay, but it can be different structures. If it has got same formula and different structures, then it is called as structural isomerism. Okay, and if it has got same molecular formula, same structure also, but the orientation or spatial arrangement is different, then it is what we call as stereo isomerism. Okay, the same molecular formula, different structural formula. Okay, and like for example, you have studied all of this in your organic also, and this year also you'll be learning all this isomers and all that. Correct? So you have a chain, the structure is only different. Sometimes the parent chain is different, sometimes the substituent gets changed here and there. Similar, basically structure is different. Then it is called as structural. And under structural you have four types. Okay, I remember it as IISC, but this I is L here, that's all. Okay, S and C. So this is ionization isomerism. We will understand all of this in detail. This L is linkage. Okay, this is solvate or hydration, and this is coordination. Okay, and when I say stereo, they will have the same structure. Okay, but same formula, of course, same structure also. That means there is no change in the what I should say, everything is the same structure wise. The only thing is the orientation is different. What do you mean by that? If you just rotate it, instead of you standing like this, maybe I'm turning and facing that way, the molecule at one side, it is in one of the isomer it is turning towards you, and in the one isomer it's turning on the back side, or the angles between the molecules atoms may be different. Okay, so we do not say it's the same a different structure. It will be still having the same structure. Okay, only the angles will be different, or only the orientation will be different, and that can be divided into geometrical and optical isomerism. Geometrical deals with the orientation. Okay, optical isomers is dealing with the what happens when light is incident, how does it orient the light. Okay, now I'll get to all those details in a while. So for now, in this video I'll be doing stereo isomerism first, then let us talk about this. Okay, so this is the overall structure. Okay, so this is about the yes, we were discussing structural. I will do it in the next video. Stereo is what we'll be doing. Stereo means what? Same molecular formula, same structure, different orientation, but because it is having different orientation, it will have different chemical and physical properties. So please remember that as well. Okay, let's start with the geometrical isomerism. Now, only when I do it in you will understand the meaning, right? So if I talk about geometrical isomerism, it has that cis and trans. Cis is when the angle is 90 degree and trans is when the angle is 180 degree. This is what you already know. But let us do it one by one. Okay. Now if you are talking about square planar complexes, let us talk about what kind of, whether do they exhibit geometrical isomerism or not. Okay, square planar means what will be the coordination number? Coordination number will be 4. All right, so if you are having this type Ma2B2, what is the meaning of that? M is the metal atom. Coordination number 4 means totally there are 4 ligands, but of 2 different types. 2 ligands of A type, 2 ligands of B type. Like for example, PT, NH3 twice and Cl2. Okay, so if you have a complex like this, the PT will be in the center. It's square planar. So what is one way you can write it? You can write NH3 here, NH3 here, Cl here and Cl here. If that is the case, you will be getting, now you can interchange this also, but ultimately the angle matters. This is what we call as a trans isomer. You will say trans, what is the name of this? A comes first, C comes first. So it is diamine, dichlorido, platinum, and the oxidation number. Okay, 2 and yeah, it will be 2. Okay, platinum 2I. That's what you will say. Okay, so next, if at all, this is not an ion, this is a compound anyways, yes. If you just shift it like this, NH3 and NH3 here on the same side, and Cl and Cl, what is this angle? This is 90 degree. This is what we call as cis isomer, cis diamine chlorido platinum 3, platinum 2. Okay, so A2B2 will show of this kind. Okay, so this is showing cis and trans. Okay, next is MA3B. Okay, MA3B will not show this isomerism. The reason is because there is nothing called cis and trans here. You have M, A3, anything in 3 and B. Look at that. Even if I change whatever position, will I get it? No, right? I can see a 90 degree and 180 degree here. So no matter you change this, I cannot get a cis and trans here. So simply remember, this will not show. And if you have M, A, B, C, D, all 4 being different, like in the case of PP, NH3, okay, sorry, NH3, Br, Cl and Py. Okay, so if you have something like this, you will have different isomers possible, correct? You can put it in any way. You just stick to ammonia and decide. With ammonia, you are having bromine, you put chlorine somewhere, you put Py somewhere. Now look at that. If you are talking about the angle between this is 180. Any one you decide, alright? And in the next case, you are having ammonia here, okay? And the 180 degree is between bromine here, and when you put chlorine, you put Py. It doesn't matter you put chlorine here, because ultimately ammonia is making 90 degree with this, ammonia is making 90 degree with this, 180 degree with bromine. Okay, and in the last you put a Py here, NH3, Cl, Br. This is also going to be 3 different possible isomers, correct? So these are the 3 different possible isomers. Okay, now that is about square planar. So this will show isomerism. Okay, what will be the, there will be 2, this will be cis, this will also be, wait, alright, 2 cis and 1 trans, correct? Yes, cis and trans, yes, 2 cis and 1 trans it will show here. Now if you are talking about tetrahedral, because for coordination number 4 you will have tetrahedral. In the case of tetrahedral, all the 4, okay, will have the same angle, correct? Now in 2D it might look, no, the angles are different, but you know it is 109 degree, 28 minutes everywhere. So it is a symmetrical molecule. No matter you change, whatever you do, the angle will still be, you will not be able to have a different angle there. So that's the reason it will not show geometrical isomerism. Okay, for coordination number 4, let me write it. For coordination number 4, if it is tetrahedral, no geometric isomerism, no. Okay, if it is square planar, then A2B2 will show, ABCD will show, A3B will not show. This is the summary. Okay, now that is about coordination number 4. What happens if the coordination number is 6? Let's talk about that. Okay, so coordination number is 6, that is octahedral. Okay, now octahedral, if you have A4B2, if you have something like this, like in the case of CONH34Cl2 plus. Okay, so cobalt is the central metal. There are how many? 4 amines, so you can have different ways to arrange it. It's octahedral, something in the plane and something out of the plane, on top and bottom. Okay, so if you fix, there are how many? 2 chlorine. So let me say chlorines are here, okay, and 4 ammonia are on the, this is a plane, okay, 4 ammonia are on the plane. So what will be the angle between chlorine? The angle between chlorine is 180 degree. This will be trans. Okay. Now here if I make chlorine here and chlorine here, then if I have ammonia, 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 ammonia here, the angle between this is 90 degree. Okay. Now don't, in 3D you visualize, it is like one chlorine is on the back here, one chlorine is on the back and one chlorine is on the top. So that angle is 90 degree. Alright, that's what I'm telling. So this is going to be cis here. Now anything else if you want to even try, like for example, if you think that chlorine will be here and chlorine will be here and then ammonia, 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 ammonia. Look at that. This is still in the plane. These 4 are in the plane, right? The angle between them is still 90. Optically may be different, but geometrically they are same. This is also going to be cis. So you will have 2 possibilities here. Okay, so A4B type definitely shows cis and trans optical isomerism. Sorry, cis and trans geometrical isomerism. Yes. Next, we are going to do AA2. If what there is a bidentate. Okay, so we write it like this. AA is a bidentate. 2B2. So 4 and 2 6. Okay, AA2B2. Alright. So now, what will be the possibilities? Central metal will be here, or for an example, let me write it CO, Cl2, En2 and Cl. Okay. So we are only bothered about this. So you have the metal here and this is my square planar. Okay. So this is nothing but cobalt here. So let me write cobalt. Now, what will be the possibilities? I can put En here, En here. They are like, you know, they are bidentate, En here, En here. And the 2 chlorines will be here. So this is going to be trans because the angle is going to be 180. Okay. And is a cis possible? I can do it, right? So I just have to fix 2 chlorine. So this will be chlorine and this will be En here. No, I cannot do it because then I cannot have 2 ENs which are binding like this, right? So I can do this. This will be Cl, this will be Cl. This is En and this is also En. No, En should be one more bottom. This is also En, correct? So look at that. This angle is 90 degrees. So this is going to be cis. So that means for this also it is fine. Alright, this also it is fine. Octahedral. Octahedral geometrical. Okay. Now anything else you do, the angle between Cl, if it is 90, then it is going to be the same thing. So do not write repeated diagrams. Just have to see what is the angle. Okay. And En here I can't do because that it will not be able to bind in that case. Okay. So that is about it. So this definitely shows. And the last type here is A3B3, geometrical isomerism for MA3B3. Okay. Like in the case of CO, NH3, 3 and NO2, 3. Okay, so if you have something like this, what will the arrangement be? Now, look at that. You have cobalt here and this is my square plane. Alright, this is my square plane. One possibility, I have 3 ammonia. So, I will fix 3 here, 1, maybe 2 and let us say 3 here. Okay. And here I will have NO2 and NO2. Now see, I cannot talk about cis and trans here, right? Because I have 3 molecules. So when there are 3 molecules, we use the word fec and mer, that is facial. Facial means if I join this and if I join this, you have 2 parallel planes, that is fec, continuous they are. Okay, and mer or meridional is when, suppose let me say NO2, they are not continuous. Okay, NO2 and let me say NO2 here, and in between you have ammonia or ammonia and ammonia. So if you draw a plane like this, they kind of intersect. That is what we call as mer. Okay, so that is about geometrical isomerism. So don't get confused. Square planar will show, tetrahedral will never show because all it is even if you rotate, the angle is going to be the same. correct? So it will never show. Tetrahedral A2B2 will show, ABCD will show, A3B will not show. In case of geometrical, these are the things which will be possible. Okay. Now let us talk about optical isomerism. So optical. See, optical isomerism means there is some kind of optical activity. Okay, so imagine you have a light. A light, if it is able to vibrate in all direction, we call this as unpolarized light. Okay, and let us say you pass it to a prism, a special kind of prism which is called as Nicol prism, that will make the light vibrate in one direction or in one plane. This is what we call as plane polarized light. Okay. Now, what I do, whatever I want to test, you know, my whatever coordination compound, this is my coordination compound solution. Okay. If this plane polarized light is made to pass through this coordination compound solution, which I want to see whether it is optical, it is having optical isomers or not. Okay. Suppose it is able to change the plane polarized light into this direction. This is what we called as dextro or R something to the right side. D something we say, not R. Okay. Right side is dextro. And suppose if it changes to the left, we call it as levo. Okay, so this is L and the name of the isomer. Okay, so generally, if you think this coordination compound is having an when do you say it is having an optical isomer? First of all, it should be able to change this state. Okay, if it is not able to do it, if the light remains like this, which is not changing left or right either ways, we say it is optically inactive. And if it is optically inactive, it will never show optical isomerism. So if the plane polarized light remains like this, that means it is optically inactive. Optically inactive means it is not showing any activity. That means it is not exhibiting optical isomerism. But suppose it is taking in this path, that means it is optically active, and we call optically active compounds as enantiomers or chiral substances. Okay, and now if it is able to show this in either one direction, that is what we call as a D if it is in the right, and the other isomer will make sure that it will be in the left. Okay, so now how do you identify this? Active, see, I cannot every time go and check in the solution, take a plane polarized light and then see, oh, okay, it is optically inactive. Oh, it is active. How do I know whether it is dextro? Oh, this is dextro. Then I take the second isomer. Oh, this is levo. I cannot do that. So I need to have a theory behind this, correct? So we do not, this is the meaning of it, that you pass it through a solution, and if it is not changing the direction, it is inactive, no optical isomers. In this case, there are optical isomers. But theoretically, how do we understand it? We say something like non-superimposable. If it is non-superimposable, like my two hands are non-superimposable, the thumb is not falling on another thumb, then that means they are optically active. And what is the meaning of non-superimposable? We can just write non-congruent or asymmetrical, correct? If there is no symmetry, that means it is non-superimposable. That means I cannot put it on top of each other. It will not fit exactly. Something is mismatching, and only such substances will be optically active. So now my job is much easier. I just have to figure out whether they are superimposable or not, or I just have to figure out whether they are symmetrical or not. Okay. If they are symmetrical, then there are two isomers which exist. If they are asymmetrical or if they are non-superimposable. Now imagine these are the two elements, they are non-superimposable. One of the isomer, if it is rotating it to the right, the other isomer or the other image, two mirror images I will have, right, which are non-superimposable. So if one of them I put it on the right side, the other one will change it to the left side. So the two optical isomers will be actually like this. So imagine if I have to actually test it, I have to put it in the solution, then see where is that direction. Okay, then conclude whether it is there or not. Or the second way, I have to get a mirror, take the image of that, and then try to place these two images and check if they are superimposable or not. Who wants to do that? Okay, imagine I give you a substance, you will take it, you will write its structure, take it in the front of mirror, then you will get a mirror image and then you will check. We don't want to do that. The best way is we check for symmetry. If it is asymmetrical, or that means it is non-superimposable. Look at that, these two are not symmetrical, correct? You know, there is, I cannot divide it in any ways. That's the reason they are non-superimposable. So I only check for symmetry. If at all it is asymmetrical, that means it is non-superimposable. That means it is optically active. That means it's just a name. They are enantiomers. The two molecules are enantiomers or they are chiral in nature. Alright. So let us understand more of this. Okay. So if you are talking about square planar, in the case of what is that? Your coordination number 4. Square planar, you can imagine, you know, there is one here, one here, one here, one here. I can see a symmetry there, right there. Okay, so I can actually cut it in this direction, and imagine it is a thick book, right? If it is a thick book, I can cut like this, right? And there is a line of symmetry. So square planar will never show optical isomerism. They will show geometrical isomerism. We have discussed A2, B2 and ABCD, but they will never show optical isomerism. Okay. Now then we are left with octahedral. In the case of octahedral, let's see, if you have MAA3, okay, so it's like cobalt, and then you have like this and like this. Let us say you have EN, EN and EN. Okay. Now I do not see any way wherein I can divide it in the form of a symmetry. So definitely this is optically, it is non-superimposable, so optically active. So what will be its mirror if you write? It will be something like this, CO. If you just mirror it, how does it look like? This part will be shifted here, correct? So this will be EN, this will be EN, this will be E. Okay, if this is dextro, this is levo. If this is dextro, this will be levo. That's all. That means it's optically active. Look at that. Otherwise, I have to, you know, see the mirror image and then check, you know, if I place, that is also one way. You can do that also. Find the mirror image, all right. You know, it's kind of, you rotate it and put it that side. And then see, they are non-superimposable, right? If you fix this on this, EN and EN are not overlapping. This EN is here and this EN is here. Non-superimposable. If they are non-superimposable, that means they are optically active. One is dextro, one is levo. Okay, so that way also you can check with the mirror or think in terms of symmetry. Okay, next, MAA2B2. Okay, like for example, in the case of cobalt, En2Cl2 plus. Okay, what is this? Coordination number 6, it's octahedral. Now think about it. What is one option? Okay, so one option is this. Okay, one option will be the chlorine and chlorine. Can I have, how many chlorines are there? There are 2 chlorines, right? So if I keep my chlorine and chlorine here, okay, and then if I have En and En, this is my En, okay, and this is my another En. Okay, so this is what? This is actually a trans isomer, and if it is a trans isomer, right, this is a trans isomer. First let's write the possibilities. If it is a trans isomer, if I take a mirror image, it is symmetrical, correct? It is superimposable. The mirror image will be exactly like this, and I can superimpose them. So that means they are optically inactive. If it is superimposable or if it is symmetrical, then it is inactive. It should be non-superimposable or asymmetrical, then only it will be optically active. So trans will never show. Now let us talk about cis. Okay, cis will be like, you know, you'll write chlorine here, and En here and En here. Okay, so if you take the mirror image, imagine there is a mirror. What will you see in this case? You will see something, this chlorine would have come here, correct? So this chlorine would have come, this chlorine will be here, this chlorine would have come here, and this En would be here, and this En would be here. here. This will shift that side, left and right. Correct? And they are not superimposable. I cannot put them, the position are not same. So this is optically active. One of them is dextro, one of them is levo. Alright, so what is the best thing for if you want to see, if they give you a compound and ask you to write all the possible isomers, first stereo structure, of course we have not done. If you are talking about stereo, first write the geometrical isomerism, then check whether the geometrical isomerism is active or not. So first write cis, this is trans and this is cis. Actually these both are same geometrically, but optically they are different, correct? Because the angle is 90-90 in both the cases. So geometrically I will have 2, okay, and if I talking about optically, this is inactive because it is superimposable. I will have these 2 isomers. Totally, one, if I am talking in geometry I have 2, in optical isomers also I have 2 because this is not there. Alright, so yes, that's how you understand isomerism. Okay, after this I will be doing the structural isomerism.